You've probably seen these equations at least once in your life. In different systems, they are known by different names, particularly in the IB system, and in some AP courses, they are known as SUVAT equations because of the variables S, U, V, A, and T. However, most people who blindly memorize these formulas take absolutely nothing away from them. And therefore, in this lesson, we will be learning how to properly derive the SUVAT equations and when not to use them. This is lesson 1 on mechanics. So, this is the first lesson on mechanics. It will be mostly about kinematics. We will talk a little bit about other things such as units and different ideas, but mainly this is going to be about kinematics, which is the idea of how objects move without considering as much about forces. Though typically kinematics is done in parallel with forces and with different accelerations, different changing accelerations even, where we have to use the integral. But in this case, we'll only be dealing with uniform kinematics. And this will probably be one of the most common ideas, whether it's in AP, in IB, or even in comp physics. And therefore, this video will serve as an all-in-one guide to basic kinematics, and hopefully a revision for the people who actually understand kinematics and just want to review how everything came to be. So let's talk about first one of the most underlooked properties or ideas in physics, right? Which most people don't actually talk about, which is position. Position, especially relative position, is very important in physics, okay? An apple situated here on this desk will have a completely different idea to an apple situated here. And let's say the desk was even more tilted. Let's say the desk was like this. Then an apple situated here will be experiencing something completely different from an apple situated here. And even more different from an apple completely under the table, right? So this is how position is important. And in kinematics, position is important as well, because in kinematics, we're looking at motion. And in motion, we're looking at the change in position. Right. So first of all, the most important idea in essentially any intro physics course, X. This we call position. Now, depending on the difficulty and the level of the physics you're studying, there's typically 3 ways to show position. One is in a one-dimensional way, right? In a one-dimensional way, we have a line, and the position is defined by how far front or back it is on the line. For example, a position here might have a value of positive 1.4. A position here may have a value of negative 0.9. And so that's how we define position for one-dimensional values. The other way where you might see position is in a two-dimensional plane, which is actually very similar to our Cartesian plane in math. So let's say we have a plane here. Then a position can be expressed using the coordinates of the point. Let's say this point has y coordinate 4 and x coordinate 3. Maybe not, maybe 5 here. Let's say that's 5, that's 4, right? Then we can express this point with position 5, 4. And the final way, which is one of the harder ways, is in 3D. we have a 3D coordinate system as such, then a point can similarly be represented using 3 values, x, y, and z. Keep in mind this x is slightly different from this x, which means position. We standardly use this x because in most position-related problems, we are talking about one-dimensional position where an object is moving along a straight line. And that's going to be most of what we cover today, because SUVAT equations are typically used only for one-dimensional motion. So now that we know what position is, what exactly is displacement? And what's its difference compared to position? And what's difference compared to distance? That's what many people care about. Displacement we typically write as S. Keep in mind this is not the unit, this is the value, right? So we have a difference between units and values. Let's say a length L, we will typically write as a variable value L. But the length is not measured in L's, it is measured in meters. So keep in mind here, displacement is not measured in S's, it's just we write S as a displacement. So S could be 1.2 meters, and meters are the units of displacement. Alright, so now what exactly is displacement? A displacement is a change in position. Keep in mind this is not a velocity, it's not a change in position relative to time, it's just a change in position. Now, how do we calculate this change in position? In one dimension, it's pretty simple, and it's pretty clear as well. In a one-dimensional number line, the change in position is just how much the position has changed. Here we can see in this direction, let's say we have a position of -3 and a position of +6. From here to here, the change in position, S, will be 9. From here to here, the change in position, S, will be -9, because it's going in the opposite direction. So the change in position is just going to be the initial position taken away from the final position, because see here we're taking 6 away from -3, so it's going to be x final minus x initial. Okay, this is for one-dimensional position changes. For two-dimensional position changes, and three-dimensional position changes are not seen often, so I won't cover them here. For two-dimensional position changes, let's say we have this point and this point. This point is x1, y1. This point is x2, y2. This is a change in position, right? And this change in position can be represented in two different ways, which we will cover later when we talk about vectors. One is to split it into the horizontal and vertical changes. So this change can be represented as the new x minus the old x and the new y minus the old y. Another way to represent this change is by using this angle. Let's call it theta, right? Then the change in position will be the magnitude of the change. So how long this guy is, and the angle, because this represents a unique change. So this will be x2 squared, x2 minus x1 squared, minus, this is by Pythagorean theorem. You can take a look at courses on the Pythagorean theorem if you have to. This is going to assume that you know basic math, right? So it's going to be equal to this in magnitude, and theta will be equal to the change So this is going to be the magnitude of this change, and the angle is just going to be equal to the inverse tangent. Again, this physics requires a basic understanding of trigonometry and Pythag, and even vectors. This is actually vector notation in math, but we won't talk too much about that. That's unimportant. But you need to know Pythag, you need to know trig. It's going to be equal to the inverse tangent of this divided by this, which is going to be y2 minus y1 over x2 minus x1. So that's how we find the change in position in 1 dimensions and in 2 dimensions. Now that we're talking about displacement, we might as well also talk about speed, right? Speed and velocity. So one of the most common trap questions in speed and velocity for physics is, what is the difference between these two? And is there a difference, right? With that, we must first define velocity. We must first look into what this is. And before we look into what this is, we need to go back to what we said about displacement, right? We need to find the difference between displacement and distance that we were talking about. So let's try to find the difference, right? This is very clearly shown on a 2D diagram, and will even more so be shown on a 3D diagram. But let's say we have this point here, and this point here, and this guy travels like this to reach this guy. Here, the distance walked, let's say this is a mountain trail, right? This is the bottom, this is the peak of the mountain, right? And let's assume they're the same height, just for convenience. From here to here, this is how much you walked along a path. And from here to here, this is a direct displacement between these 2 points. So the displacement is the shortest possible path between the 2 points, while the distance is how much you actually go. And this is a clear distinction for speed and velocity, as velocity is how much we went, so how much we changed in position, divided by how much we've changed in time. And by definition, how much we've changed in position is displacement, divided by how much we've changed in time. So this is the formula for velocity. Alternatively, you might see this as s over t, because the delta is not really important, because the change in time is sometimes just the time elapsed. Alternatively, you might also see something that looks like this. Here, dv equals dx over dt. This is calculus notation. Essentially what it means is the velocity at an infinitely small point is equal to the velocity at the tiny displacement you go through, divided by the tiny amount of time you took to take that distance. And this will be shown a little bit later in graphs. We won't show that for now. This is probably going to be the most common form you encounter, alongside, like I said, s over t. Some write x over t for if you begin at 0. There's also d over t, though this can get confused with distance, so most people prefer writing s over t. Now, the exact alternative to velocity is speed, which is distance over time. And we don't usually have a symbol for distance. It could be d, like I said. It also could be anything you arbitrarily define. You can call it k, right? The reason why we don't have a nice variable for distance is because we don't see it often, right? Usually and in infinitely small amounts of distance, right? Let's say this is very, very tiny. This and this make less of a difference. And the closer you are, the less the path actually matters, right? So distance and displacement actually are equivalent at smaller, well, infinitely small lengths. So usually we don't have a nice symbol for distance. So perhaps we go back to what we have so far. What we have defined so far is the notion of position, the notion of displacement, which is the change in position, which is written as s, velocity, which is the rate of change of distance over time, right? And we've also talked about speed and distance, which we will not talk about in the vast majority of physics. There's also another very common value that we'll see, and also time, obviously. Right? The units for these respectively, position doesn't have a unit, but typically in a chart, right, you'll have how many meters, right? So technically the unit for position is meters. For displacement, it's also meters or centimeters or millimeters, right, depending on how much you're looking at. For velocity, it will be meters over seconds or any equivalent idea, like it could be km over 3600 seconds, which will just be kmh, right? It could be meters per minute, so it could be meters per 60 seconds, but the fundamental units are the same. So meters per second, and time will just be seconds, right? And then we have a new final value that we want to introduce called acceleration. And acceleration is seen very commonly in daily life. That's why we have a very nice name for it, because it's how quickly velocity changes. Because velocity is how fast the thing moves, right? Let's say there's a ball rolling towards you at a constant velocity, but that's not always the case. Let's say the guy threw the ball at you, then it will start from 0 velocity. It will go a little faster, it will go more faster, and it will go very fast until it smacks you in the face. So that's acceleration, right? And acceleration is how fast velocity changes with respect to time. So it's how fast velocity changes with respect to time, and that will be delta v over delta t, which can alternatively just be written as v over t. Sometimes, again, some people don't write the delta. It's better to write the delta. Most books or papers prefer you write the delta, but v over t is just fine as well. And then therefore the units is going to be the units of velocity, which is meters per second, divided by the units of time, which is seconds, which is going to be meters divided by 2 seconds, like 2 pieces of seconds, right, which is going to be meters per second squared. And that is the units for acceleration. And now that we have all 4 core values down, right, maybe we should talk a little about how this has to do with SUVAT, although we're not going to get into SUVAT itself yet. As you can tell already, displacement is s. Velocity has u and v for initial and final velocities, respectively. Time has t, and acceleration has a. Hence, we have now found all the guys who come into play in SUVAT, right? And what SUVAT basically does is it relates all of these values to each other when acceleration is constant, when this guy is constant. If this guy is not constant, you need to ask calculus, okay? And that is most likely going to be covered in the future if you take AP CMEC or if you take IB Physics HL. But that requires calculus. Okay, so now that we have everything we need for SUVAT, we need one final thing before we can get to SUVAT itself. And this final thing is going to be a chart or a graph, right? And graphs are only seen in one-dimensional motion. So let's say we have a graph here. Boom, boom. Graphs are only seen in one-dimensional motion. The most common type of graph that you'll see in this stage is going to be the XT graph, which is the position time graph. Okay? Most of the time they assume the initial position is 0 because for convenience sake, let's say this guy starts moving at 0 because you wouldn't randomly say this guy starts moving at 2000, right? Unless you're defining 2000 for something important. Let's say 2000 was his house. Then he could be starting at 2000 because 2000 might be his school. But otherwise, you would define 0 as where he starts because it's the most important position, right? And the graph might look something like this. And what does this show, right? It shows, well, first of all, when it's positive, it means he's going forwards from his position. So recall the number line. He's going forwards from his position, okay? If the graph falls down to the negatives here, he's going backwards from his position, right? From his initial position. So this motion would look a bit like he goes up, and then you can see he comes back down closer, and then he goes back up, right here, and then he comes back down closer, and then he goes back up and down, goes back up and down all the way to the end, and then he comes back up, and then he comes back down. So that's how this graph will look like in motion, just to illustrate a point, right? Now, let's first take a look at this graph, because this one is probably one of the most key ones. This is a straight line of x with respect to t, right? We can see every time we move a constant bit of x, a constant bit of t, there's a constant bit of x, right? So if we move another constant bit of t, there will be an equal constant bit of x, right? And so what does this mean? This means, well, remember, this is how much x we've gone, and this is how much t we've gone. And so the slope of this guy is going to be how much x we've gone divided by how much t we've gone, which is, in fact, going to be the velocity. And here we also have an equal bit of x, an equal bit of t, and so this one will also have slope v. So a line with a constant slope has the slope v. And this is what we call in calculus a derivative. So let's say we have a curve like this, right? How do we approximate its velocity at this point, right? So this would look a bit like, again, if you don't know what this will look like on a number line, this will look like I start from here and I go and I go, and then here this bit goes this much x, and here this bit goes way more x, right? So here we can see this will look like I go slowly, 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 and then now in 1 second I go more, and then in 1 second I go even more, and I go even more. So it's accelerating motion, right? And how do we find the velocity at different points? Well, in calculus, we do something called a derivative. We find a line tangent to this point, right, which is like essentially just close to this point, is approximation, and then we find the slope of this line. So this line has this slope. Let's say at this point the velocity will be like this. And this line has less of a slope, meaning the velocity at this point is less than the velocity at this point. Now here, we obviously have an even higher slope right here. And this means, well, at this point we have a higher velocity than at this point, which has a higher velocity than at this point. We can also take a look at some other curves. Let's say this curve. What does this curve entail? Well, it shows you at first you have a high velocity. At here your velocity becomes 0. Then the velocity becomes negative. So on the number line, at first the velocity is positive, then it becomes 0 for a brief moment before becoming negative, right? You need to remember the position is still in front of the original position, right? Because it's still positive. So the position is still in front of the original position, but the position relative to this one, so here, has decreased, right? And then here we can see that eventually it becomes 0 again before it reaches the initial point, and then it goes back up. So that's what this graph will look like, right? Perhaps we'll get rid of all this. And let's take a look again, one final xt graph, right? This one. Well, maybe a better drawn one. This one, right? Here again, initially we have a positive velocity. We end up at 0 velocity. We go down, backwards, backwards, until we go past the initial point, and then we have a 0 velocity, and then we have a positive velocity. So here we can see on the line, we have started from here, we have a positive velocity, we have a 0 velocity, we have negative until we're behind the original point, and then we have a positive velocity. And that's what we can see with the slopes and calculus telling us about derivatives. And calculus also gives us one more cool little thing called integrals. So let's try something first. So we've shown this very common graph, right? We've shown this very common graph. We haven't shown yet this very common graph. And what does this graph mean if this line is completely horizontal? Well, this graph means that the position never changes. So the position has always been here at some fixed point, right? And let's say the position has always been here at the fixed point. Then the slope here will just be 0. And so we know that a flat line has a slope 0. This can again be proven using math. And because a flat line has slope 0, it will have velocity 0. And that's the first type of graph, the xt graph. There's not much to talk about here. Let's talk about something more interesting. The other type of graph that you'll encounter at this level is the vt graph. Similarly to the xt graph, we can have a line that looks like this. And because we have a line that looks like this, and this is a change in t, and this is a change in v, we know that this slope is just going to be delta v over delta t, which is the change in velocity over the change in time, which is going to be acceleration. So the slope of this line is going to be accelerations, right? Let's talk about this then. And there's a bunch of common misconceptions here. Let's say we have this line, or even this line, right? Some people will say, okay, cool. We have our number line. Well, not our number line, our position line. This is the initial point. And then at first, he accelerates. As you can see here, he goes faster and faster and faster. And then he slows down. And then, his velocity becomes negative. And then you see he goes below the initial position. So he goes here and then he goes back up. But this is wrong, right? This is completely wrong. Why? Because this is no longer position. This does not mean he goes below the original position. This means he goes below 0 for velocity, not below 0 for position. So here what actually happens is he goes faster and faster and faster until here, and then he slows down, right? He slows down until his velocity reaches 0, and then he goes backwards a bit, and then he goes forwards again. So he goes backwards a bit, then he goes forwards again, and that's what's happening in this diagram, right? Now, the interesting thing about VT graphs with a horizontal line is they're slightly different from XT graphs. They don't mean nothing. Why? Because that means the object is moving at a constant velocity, right? And a constant velocity means, well, equal intervals of time, right, yield in equal intervals of velocity. So let's say the velocity here is going to be v, just this guy, because v is always constant. Let's say we pass through 1 second, right? Then how much would this go through? How much distance or displacement has it went through? It's went through, let's say v is, let's give a more concrete example. Let's say v is 2 meters per second. And let's say we went through 1 second already. Then here, at this point in time, he's went through 2 meters per second times 1 second, which is 2 meters. Let's say we go 1 more second. Similarly, here, it's also went 2 meters. Let's say we go 2 seconds extra. Then at this point in time, he's went 2 meters per second times 2 seconds is 4 meters, etc., right? And what we can show here is that, well, in fact, the displacement went through in this interval of time is the area of this cool little rectangle, right? And so here, let's say the velocity suddenly shoots up for absolutely no reason to 3 meters per second, right? And we go through 2 seconds of time. Then how much does he go in this time? 3 meters per second times 2 seconds, he goes through 6 meters. And that's, again, the area of this rectangle, which means for any given function, we can approximate how much he's went, and in some cases not even approximate, right, using rectangles. So let's say we have this curve, the amount of displacement he's went is equal to this rectangle, like let's assume these are infinitely thin, right, plus this rectangle, plus this rectangle, plus this rectangle, plus this rectangle, plus this one, etc., etc., right? And in some cases, we can just directly calculate the area after approximating. This rectangle, plus this rectangle, plus this rectangle, plus this rectangle, etc., etc., which is just going to be the area of the triangle. So we call this the area under the curve, the AUC, okay, also known as the integral, right? And what the integral does is it calculates the area under the curve, and in physics, this area under the curve means, especially in a VT graph, In a VT graph, it specifically means the displacement traveled. All right. So let's say we go this much. All right, let's say we've went for 2 seconds, and the velocity begins at 0 meters per second and finishes at 5 meters per second. Then the total displacement will just be the area of this triangle, which is 5 times 2 divided by 2, so he will have went 5 meters. An alternative way to work on this problem, which is a way that I like that is more intuitive, is that this area is equal to this area. So this movement is actually equivalent to having a constant velocity of 2.5 meters per second. And that is 2.5 times 2, which is 5 meters. Both are valid, right? And so now we have shown that in the two key graphs, in a VT graph, we can find acceleration, and we can also find displacement. And we have also shown in displacement time graph, we can show, we can find velocity, right? And here's where we can actually find SUVAT. First of all, the first SUVAT equation says that the final velocity is equal to the initial velocity plus acceleration times time. Now, what is the definition of velocity? It is what is the definition of acceleration? Sorry. Acceleration is equal to change in velocity divided by change in time. The change in velocity, by definition, is the velocity that we end with minus the velocity we begin with, right? So acceleration is equal to Vf minus Vi over delta t. Now, in SUVAT, we like to use V as the final velocity and U as the initial velocity. So we write acceleration equals, from our equation that we derived this from, right, is equal to V minus U divided by T, right? And then we multiply the T over, and we get AT is equal to AT is equal to V minus U. And then we move this over, and we have U plus AT equals V. And this is intuitive, because the initial velocity times how much we've changed in velocity is going to be equal to the final velocity. And that's the first SUVAT equation. It's not that complicated. And the second SUVAT equation states that V squared minus U squared equals 2AX. 2AS. Yeah, I like to write this as delta x. It's more useful in that case. This we will skip for now. This is actually the hardest SUVAT equation to prove using intuition. I advise this to be one of the two SUVAT equations that you memorize. But the third one is not that difficult. The third one says that, well, the displacement is equal to ut plus half of at squared. Remember that in SUVAT equations, we're assuming a is constant, right? Then we can just draw out a diagram. It's not that complicated. We have a diagram. We have a graph here. This is the initial velocity u, right? This is the final velocity v. We connect these 2 points, and then the displacement, the change in position, will just going to be the area of this trapezoid, right? And this trapezoid has time change t, and we can easily see that is equal to u times t, which is this rectangle here, boom, plus half of at squared, which is actually the triangle up here. Why is it the triangle up here? Well, from SUVAT equation number 1, we know that v is u plus at, so we know this bit is at, and we know this bit is t, right? And the area of this triangle is at times t divided by 2. So the area of this triangle is in fact the half at squared part. Now, the third SUVAT equation is structurally equivalent to the fourth SUVAT equation. The fourth SUVAT equation states that S is equal to Vt minus half of At squared. And why are these two structurally equivalent? Well, you're just doing a different auxiliary construction. You can connect this to here, and you know that the big rectangle, so instead of calculating this small rectangle, right, instead of calculating this guy, after this construction, we see that the big rectangle up here, this big guy, so the entire thing, right, this entire thing, this guy has v times t. And we also see this area of this triangle is actually equal to the area of the triangle we just calculated, which is half at squared. So it's just going to be vt minus half at squared. And we have proved, just using what we have learned so far, the first SUVAT equation, the third SUVAT equation, and the fourth SUVAT equation. The fifth SUVAT equation is even more simple, and it says that the displacement is equal to half of u plus v times t. And that's actually very simple. That is one of the ideas I told you before about how to get the triangle area, right? So here we have we have a nice triangle, which is this trapezoid, right? And then to get the triangle area, we can actually draw a line through the middle, which is the average, right? Which is v plus u divided by 2. And then we show that this triangle this extra part here can be moved to here. And so the displacement is just equal to this rectangle, this rectangle here. Right, and after we show that it's equal to this, it's just going to be u plus v over 2 multiplied by t, which is just going to be the fifth SUVAT equation, which is s is equal to half of u plus v times t. Right, and this is also the same as the area formula of a trapezoid. I just wanted to show the shifting parts around idea here. This will be a little hard to prove. We'll prove this on the next page. And before we prove that, I just want to clarify one thing I forgot to clarify, which is for the area under the curve, we have negative areas as well. So let's say we go like this, right? There's going to be a positive area up here. There's going to be positive areas up here, but there's also negative areas. So this is negative displacement, right, in the VT graph. So this part corresponds to going backwards, while this part corresponds to going forwards. Just keep that in mind. Now moving on to the proof of the SUVAT equation number 2, and this will be the end of today. B squared minus u squared equals to 2as, and this is what we want to prove, right? This is probably going to be one of the most important SUVAT equations you'll need to know, and it's actually easily proven using the factorization. So we have v minus u times v plus u is equal to 2as, right? This is what we want to prove. Right, this is equivalent to what we want to prove. And then v minus u from the first SUVAT equation is just going to be a times t. V plus u, right, is just going to be the average velocity divided by 2, right? So it's going to be at multiplied by average velocity over 2. Now t times the average velocity over 2, t times velocity is just going to be displacement over 2 times a, right? Sorry, this is average velocity times 2, not divided by 2. That's my fault. Times 2, and this will be a times s times 2, which will be 2as. And we have proven the second SUVAT equation. And this one requires a little bit of math, not too much on actual physics knowledge. It's structurally equivalent to the other SUVAT equations. And now you just need to know when to use the SUVAT equations. So I don't want to rewrite them out, right? But I'll find the SUVAT equations. So these are the SUVAT equations. The first one is used when you don't have displacement, when you don't have s. The second one is used when you don't have v. So when you don't have v and you want to find s. This one is if you don't have s and you want to find v. This one is if you don't have t and you want to find one of these three. This one is if you don't have acceleration and you want to find one of s or t. And the final one is if you don't have u and you want to find s. And again, I highly advise you to not memorize these, right? These are only really needed for very basic physics problems, right? For higher level and harder physics problems, it's more advised to just use diagrams and to use different equations you have using basic principles. We call these first principles, right? First principles. And we typically use first principles thinking to deal with physics problems. So try not to memorize the SUVAT equations, maybe except for the second one, which I think is okay to memorize. Everything else is trivially proven. All right, thanks. See you on the other side.